Download this code from codegive.com, link in the description below. From source code to machine code, building your own compiler, simplified. This tutorial provides a simplified overview of the compilation process, from high-level source code to executable machine code. We won't build a full-fledged compiler, that's a massive undertaking, but we'll create a rudimentary compiler for a very small subset of a programming language to illustrate the core concepts. We'll focus on a simple language that only supports addition and variable assignment. 1. Lexical analysis, scanning. The first step is to break down the source code into meaningful units called tokens. Think of tokens as the basic building blocks of the language, keywords, like let, identifiers, variable names, operators, plus, smiley face, and literals, numbers. Let's consider a simple language definition. This is a context-free grammar, CFG, defining the structure of our language. We won't formally parse it, but it guides our lexer. Python code for a simple lexical analyzer. 2. Syntax analysis, parsing. The parser takes the stream of tokens and checks if they conform to the grammar of the language. A common approach is to use a recursive descent parser or a parser generator like Antilra or Yak/Bison. For simplicity, we'll skip a formal parser in this example and assume the lexer produces a token stream in a suitable order for direct interpretation. 3. Semantic analysis ***. This phase checks the meaning of the code. Does it make sense? Are variable types correct? Are there any undefined variables? We'll perform simple semantic analysis in our simplified example. 4. Intermediate representation, IR. The compiler translates the source code into an intermediate representation, IR, a lower-level representation that's easier to optimize and translate to machine code. A common IR is 3 address code, TAC. 5. Code generation ***. This is where the IR is translated into machine code. This involves selecting appropriate instructions for the target architecture, example x86, ARM. We'll use a very simplified assembly-like representation for demonstration purposes. Simplified compiler in Python ***. 6. Optimization ***. Optimizations can significantly improve the performance of the generated code. This could involve things like constant folding, dead code elimination, and register allocation. We've skipped optimization in this simplified example. 7. Assembler and linker ***. The assembler translates the assembly code into machine code, binary instructions. The linker combines multiple object files, if the program is made up of multiple source files, into a single executable file. Important considerations ***. Error handling ***. A real compiler needs robust error handling. Our example is very basic. Memory management ***. A real compiler manages memory allocation and deal location. Target architecture ***. The code generation phase is highly dependent on the target CPU architecture. Complex language features ***. Handling features like loops, functions, pointers, and object-oriented programming requires significantly more complex techniques. This tutorial provides a glimpse into the complex process of compiling source code to machine code. Building a full compiler is a substantial project, but understanding the fundamental stages is crucial to appreciating how software works. This simplified example illustrates the basic pipeline but leaves out many important details necessary for a real-world compiler. Remember to consult resources on compiler design and construction for a more in-depth understanding.